All right. Hi, everyone. Thanks for joining me. Hope you all are having a good week. This is going to be a talk about Minigo, which is kind of the story of a 20% project that has gotten a little out of control. Goodness, there's a lot of you out there. So thanks all for coming. So let's start, I guess, with the question of what is Minigo? And Minigo is an open source independent implementation of the AlphaZero algorithm. So can I get a quick show of hands of everybody who's heard of AlphaZero? That is a lot of hands. That's great. So the AlphaZero algorithm was published in Nature. It's the first Go AI to beat a professional human. And so this talk, we're going to cover what is Minigo, what is Go itself, a quick little introduction to machine learning, because this is a cloud convention. I don't want to assume that we're going to do sort of a whirlwind tour of machine learning and how it applies to Minigo. But what we're really here to talk about is how we were able to bring this to scale on the Google Cloud Platform. And then I'm going to do a demo and talk a little bit about the things that we learned, and hopefully this will be useful. So to start, what is Minigo? Where can you find it? It's on GitHub. You can check it out there. It's under TensorFlow, github.com, or there, I guess, github.com/TensorFlow/Minigo. Feel free to check it out, send pull requests. Again, this is not an official Google project. I need to emphasize right here at the beginning that Minigo is not AlphaGo. We're not affiliated with Deepmind. We're not associated with Deepmind. And I've coded this entirely from just their published work. I don't have access to their source code, and I haven't used their source code to verify it. So why did I do this at all? If Deepmind has created AlphaGo, why did I need to make Minigo? Well, for starters, I'm a Go player. In addition to being a software engineer at Google, I also volunteer for the American Go Association, where I serve on the board of directors, and have worked for American Go for almost a dozen years now. I've been playing Go for a substantial portion of my life, and I love it. And AlphaGo is amazing. Imagine if you're a Go player and an alien intelligence has been created and it happens to speak your language. And that's Go players. We were really excited about AlphaGo, but of course, AlphaGo retired. So I felt like maybe I should take a shot at trying to create this. So there's a lot of things that I think that as Go players we can do and learn from AlphaGo. And so there's sort of a rich vein here to explore and to mine. So our goals for Minigo were to reproduce the results and provide a clear, legible example of the program. If you do check it out on GitHub, and I hope that you do, it's only about 2,000 lines of Python, which is pretty cool for a world-changing algorithm. I hope also that this can showcase and demonstrate what the power of Google Cloud can do, because this was basically a couple of engineers in their 20% time and their spare time trying to implement this. And the only way that we were going to be able to do that was by using the longest lever arm we can find. And so leverage as a verb kind of means a different thing, but quite literally here I mean it as a force multiplier for what is a very small software engineering team. So where did Minigo come from? So AlphaGo and Deepmind has been described in 3 papers. The first paper describes AlphaGo, and that is the mastering the game of Go with deep neural networks and tree search. It was published in Nature. And my friend Brian Lee wrote something called MuGo, or MicroGo, which was an implementation of that first version of the paper. He had sort of a skeleton implementation of it. It implemented 1/2 of the network, but not the other half, and was sort of like a proof of concept. So after AlphaGo, their second paper was called AlphaZero. And AlphaZero describes an algorithm that started from nothing, from random noise, and then went on to teach itself how to play Go. So mixing in AlphaZero's paper plus my friend Brian's implementation of MuGo, we get Minigo. And if you're curious about why Minigo's logo is a happy-looking robot falling off of a ladder, all will become clear. I will explain why he looks completely at ease with this situation where he's falling off of a ladder. All right, so let's talk about what the game of Go is. How many people have played Go? Anybody here? Wow, that's a lot of people. How many people like to play Go? Yes, that's exactly what I like to hear. I love Go. I've been playing Go for a long time. I really like it. So we're going to do a quick demo of what Go is. This is what it looks like at the beginning. People take turns putting stones down on the board, trying to surround territory. When we talk about capturing looks like this. When stones are completely surrounded, they get taken off the board. That also works on larger chains of stones. So you can see that groups that are connected orthogonally share their fate, where they will hang or stand together, as it were. The winner is decided by, as you try to divide up the board, whoever has more territory wins. That's it. So it's like you're drawing up lines on a map. You're carving up, I get this, you get that. You can see on the right diagram there that white has surrounded all the triangled points and black has surrounded all the squared points. This means that Go is not really a sort of absolutist game where you have to like capture the enemy king or completely destroy the enemy army. It's more like you're negotiating an agreement where you just want to get a little bit more than the other person. And this is an example of what a whole game might look like. So this is Minigo in action. You can see it sketching out territory, starting in the corners. And this pattern that you see happening right there, that is called a ladder. Ladders are an interesting example of why Go is hard. So this is a fairly straightforward pattern. You can see it develop again. It's a really obvious pattern. It's a pattern that toddlers can probably follow and predict. But it's an example where Go has a very long horizon effect, where the result of that ladder could decide the outcome of the game, and it may require looking 80 to 90 moves ahead. And so why is that hard? So a ladder is this great example of a game where you have, where even with a branching factor of only looking at 2 moves for each of those cases, you're already looking at 80 squared, or 2 to the 80th, excuse me, possible positions. So that very high branching factor makes things really difficult. The games are really long. The end condition is really hard to describe. So with Go, with chess, when the king is captured or checkmated, the game is over. And everybody can see and agree this game has ended. With Go, the game is only over when both players agree that there's nothing left on the board worth contesting. This is pretty difficult if you're trying to teach a computer how the game is over. And in fact, just scoring the board, just knowing that it is time to score the board, is a really hard problem. And then lastly, and this is possibly the most important part, is that it's really hard in Go to determine who's winning in the middle of the game. This is one of the, so this problem, who's winning, who's going to win, one of the hardest problems we have. Dealing with the branching factor, that there's so many possible moves at every point, one of the really difficult problems that we need to solve. And so let's take a step back and let's talk about how we're going to approach this with machine learning. So this is 5 slides about machine learning. Obviously, this is not an exhaustive explanation. I should mention also, this is probably a good time, none of us have PhDs on the Minigo team. So there's probably people in this audience who understand this better than I do. But bear with me. I hope that this will be enlightening for folks who have maybe not done any machine learning before at all. So real quick, inference for neural networks. So the basic idea is we're going to put in an input and get out an output. And that thing in the middle is the model that we talk about. We don't really want to worry too much about what it is, except for we need to know a couple of things about it. The first is that it's a bunch of math that is differentiable, or close enough to differentiable. And the second is that it's really slow, like slow on the order of milliseconds to evaluate. And why does that matter that it takes milliseconds? It seems pretty fast. Well, because you maybe need to do thousands of those before you can decide on a move that you play. So we're going to consider neural networks for inference. Inference meaning this forward path where we start at our input and we get out our decision. That's what inference is. It's also called a forward pass. And we need to know that it's slow and it's differentiable. All right, so how do we create that model, that thing in the middle? Well, what we're going to do is we're going to try and quantify the error, where we have inputs that we know and outputs that we should have gotten, and we're going to take a look at the difference between those and try and change the model, which is differentiable, so we know which direction we need to push the different values in that model, to make the error smaller. So that's basically machine learning in a nutshell, or at least the stochastic gradient descent form of machine learning. But yeah, it's a pile of linear algebra, and we're going to try to tweak it. And we can repeat this process where we try and make the error slightly smaller until we run out of data. That function, that model in the middle, could be a function of many, many millions of variables. So we're essentially trying to minimize the loss of million variable functions. And that's pretty complicated, but luckily there are pretty good abstractions for doing all this stuff. So let's keep going. So what is inference for Minigo, and how are we going to use that to solve this problem? So inference for Minigo in this case means 2 questions. What move should we play? Who do we think is going to win? So given that board that you see on the left, that's our input. And we're going to ask Minigo for a probability distribution of where it thinks the next move is going to be. And we're also going to ask it for a number that expresses who it thinks is going to win. So Minigo uses -1 for if white is going to win, and +1 if black is going to win. 0 says way too close to call, perfectly balanced. And anywhere in there, from -1 to 1, is it quantifying who it thinks is going to win. So given those 2 outputs, what is the move that we think is going to be played? Who do we think is going to win? We do something called Monte Carlo tree search. My friend Brian Lee, who I mentioned, wrote Minigo, did a great talk at PyCon 2018 called A Deep Dive into Monte Carlo Tree Search with code. Also, our code is on GitHub. The Monte Carlo Tree Search is really great, super easy to read, highly recommended. So that deep dive into Monte Carlo Tree Search is great. So by doing this self-play with Monte Carlo Tree Search, we're able to do to quantify our error. So we asked Minigo for what move to play and who was ahead. And now we can define our error as the sum of the difference between the original estimate for what move to play and the moves that were actually explored by tree search. So we use that estimate of who's going to win to decide whether we continue to explore that move. So we'll look at this move, then we'll look at the next most likely one under it, and if it's better or worse, maybe we won't explore that parent move. Does that make sense? Kind of, maybe? Can we just sort of acknowledge that this could happen, and we can dig into the details at some later point? All right, so that's Monte Carlo tree search. Which move and who's ahead? The 2 components, which move and who's ahead, are called the policy and the value outputs of the neural network. So policy is a given a board state, where do I think the next play is going to be? And value is how do I value this board? All right, so let's do the quick recap. That was our 5th slide, so this is our summary slide. This is how I get 6 slides. This is our reinforcement learning recap. The Lightning version of reinforcement learning is using our data to make models, using our models then to make more data, and now we never run out of data, and we can keep doing this as much as we want. So what's the model? The model is that pile of math that we had in the middle. We want to be able to measure that loss by comparing it with answers that we know or with answers that we think we know. We train a model by minimizing that error. And Minigo uses the policy and value to do tree search to try and refine its original estimates. Does that make sense? Maybe? Somebody? Yeah? No? OK, well, we're just going to move on. The reinforcement learning loop, pretty simple. It's this nice virtuous cycle that we can set up where self-play makes better data, and we use that in training to make better models, and they reinforce each other. The problem is that I've made one of those errors substantially larger, and that's not an accident, because the idea is that doing tree search involves doing many of these inferences or forward passes. We want to do as many readouts as we need to be able to ensure that we're improving our policy. And that means doing maybe hundreds or thousands of inferences per each move. Now, if we can train on each move, that means we're doing hundreds or thousands of inferences per training data point that we make. So at a minimum, we're going to have this ratio where we need to do hundreds to 1 in terms of making inferences versus making training steps. Does that sort of set up the problem here? So in order to train adequately, I need to do this for millions of games. And I know that a game will take on the order of minutes, even when I'm using GPUs or TPUs. So my question becomes, how do I scale this? Now, happily, this is a problem that is, to borrow someone's phrase, embarrassingly parallel. Having 2 copies of Minigo play each other does not involve any other copies of Minigo, which means that I can spin up as many of these as I can, assuming I have a good way to shard this all out or scale this all out. And so that brings us to the part of the talk that I think we're all here for, which is using this on Google Cloud. So we used Kubernetes to do this, but we started by making the smallest possible units of work that we could. So our training job was pretty straightforward, and we made our worker job use cloud storage as a way to sort of coordinate what we needed to do. This worked really well. Cloud storage, as it turns out, is incredibly flexible, and you can abuse it in all sorts of interesting ways. We were able to use cloud storage to get this sort of tracer bullet while we're sort of deciding, do we need to write a centralized server? Do these need to talk to a server at all? And cloud storage basically scaled to the point that we didn't really bother. So it stood up wonderfully, and we've been able to use that probably beyond the limits that we certainly thought we could. So then what we did was we turned this into containers. So we used Docker to build containers for that self-play worker. And we used Kubernetes to scale this out to thousands of nodes. So we did this. We could start up. We could fetch the latest model. We could write out our data. We could shut down and start up again. And since each time we're fetching the latest version of the model, we're always able to coordinate and make sure that we're generating new data with the latest and best model that we have. So what we originally did was we originally wrote this on a smaller board size. So the original diagrams that I showed you at the beginning were Go being played on a 19 by 19 board. That is the full-size game of Go. Go is also played on a 9 by 9 board. And this 9 by 9 board is a lot simpler. The model for that is about 250 times faster. So we were able to sort of verify correctness using that smaller model on a smaller Go board. And I'm using correctness very loosely because as it turns out, machine learning is very good at finding patterns in your data or patterns in your data that you didn't mean to put there. It's very good at covering up for mistakes that you make. So we saw something get better on our smaller size board that had really glaring, horrible bugs that we wouldn't discover until later, but more on that. The next thing we did, so after we did this and verified our correctness on the smaller board, we realized that, holy cow, the full-size model is going to be 250 times slower. We need to add accelerators. And so we were able to hook up GPUs with a minimum of fuss. We were running a cluster of about 2,100 GPUs with no problem at all. Using GPUs on Kubernetes is fantastic. It means we don't have to worry about drivers. We didn't have to make any code changes. What ran on our workstation would run perfectly on Kubernetes, on Kubernetes Engine. And this was a pretty great success, but it was still a little slow. We had some benchmark performance numbers that we were trying to hit. So the numbers in the AlphaGo paper detailed that they were able to perform 1,600 inferences in 0.4 seconds. We were about 40 times slower than that, which is OK for a solution that was Python and for our accelerators, which were not TPUs. But 40 times slower meant 40 times slower. They were able to play 5 million games in 3 days. And if we are 40 times slower than that, I'm looking at this taking 3 months. So that's a little challenging. I needed to find a way to do this more faster. So before we do that, let's take a little step and say that as I'm setting this up on GPUs and I'm realizing that this is going to take months to run, I really wanted to find ways to verify that everything was working. So with containers, it was really easy for me to make variations on the jobs I was running and really try to run other sorts of evaluation matches. It was really easy to use the Kubernetes Engine API to spin up jobs that were variants so I could test different versions of models, make sure that I'm making progress. This was a really important thing that I'm going to come back to later. And when I say measuring performance, I am measuring performance on my task, which is, are my models actually getting better at playing Go? That's a real question. So early on, I knew that this was going to take 3 months. At the point that cloud TPUs were being developed, I said, hey, this might work really well if I could try running this on cloud TPUs. And the cloud TPU team was pretty enthusiastic, and they said, yeah, sure, go right ahead. But they were so much faster that it meant really reevaluating how I had originally written my pipeline. For reference, the 2,000 GPUs that I was using were a few generations old, so I'm deliberately avoiding making any sort of direct numerical comparison. But suffice to say that what was previously fine in Python was now no longer fine using a cloud TPU. There was no way that the code was going to be fast enough, which meant that if I was going to be able to use these TPUs effectively, I would need to seriously rethink how this pipeline was going to run. When you're planning on something taking 3 months and now you're looking at maybe a week or two, you have some very different constraints about how long you can take to pre-process your input data, how long you can take to lazily push out the results of the new models, all that sort of thing. So what we had to do was we had to rewrite 4 TPUs. This code is Monte Carlo tree search. This is the short pseudocode for Monte Carlo tree search. And I'd like to draw your attention to that line that says neuralnet.evaluate leaf.gamestate, because that is the one that suddenly, this whole thing needed to go in parallel, and it needed to go in parallel a lot faster than it could. And so this was the part that the engine that would do this rapidly was the part that we needed to rewrite. So that's what it looks like on a single-threaded version. This is pretty close to what the Python code actually looks like in Minigo today. And so rewriting it for TPUs involved breaking this out into a multi-threaded version. A friend of mine volunteered to do this C++ rewrite, and he's probably not going to like me telling this story, but he was able to write this complete multi-threaded implementation, no problem, no bugs, doing a full rewrite, multi-threaded code, no bugs, no race conditions, no problems like that. But he had forgotten to actually increment a loop and was left with a brutal bug that took days to debug. It was like, oh, I'm so bad. I'm like, you just did a complete rewrite of multi-threaded code that had no bugs the first time. You're going to be hard on yourself for that? Anyway. So this is what it looked like. We ended up building a container out of our C++ port that would spin up a Python engine, and we would do these RPC calls when our queue had enough nodes in it to run them all through the model. And this did great. It also meant that our C++ code no longer depended on TensorFlow, so we didn't have to have any trouble building TensorFlow, which made our builds a lot quicker, which is pretty cool. And once we had this engine, now we could change to using deployments on Kubernetes Engine. Previously, when we were using GPUs, we used the batch API. Got a quick show of hands, people who've used Kubernetes before in this room? Cool, cool, that's great. The batch API worked really well. With 2,000 nodes, we had some interesting limits around tracking completions, and what we ended up doing was not bothering. We ended up writing our job as a job where we set something like 100,000 completions. And what that would actually do is it would throw away completions after about 1,000, which meant that it would just run constantly, which was what we wanted. The completions, writing it as a batch API worked really well because that meant that it would just always retry. It would handle the retry logic for us. That all worked really well. But now with cloud TPUs, we didn't want to pay the price of having the containers go down and come up again. So we rewrote them to be long-running jobs as deployments, and this all worked really well. We didn't need to track completions anymore because we were writing these as long-running jobs. And so this all just basically worked out of the box. One of the advantages of Minigo is that we were able to test this. So Minigo is entirely public. It's all available on GitHub, which meant that throughout this entire project, I was following the exact same path that external customers would follow. So although I'm a Googler, I basically was going through the exact same process that anybody in this room would have if they tried to go through it. And that was a pretty great experience. Honestly, I hit way fewer, and also a lot of these were while these products were pre-alpha or getting ready for alpha. And the experience was honestly amazing. Cloud TPUs on Kubernetes Engine have basically worked out of the box. Ditto for the GPUs. Like I said, the driver problems were not even a thing that I had to worry about. So if you're thinking about doing ML or accelerated computing on Kubernetes Engine, I basically only have good things to say about it. So that's pretty great. So let me do a quick demo of Minigo. I think there's a way for me to make this play, but I don't know what it is. There we go. That looks like it. So this is Minigo thinking about this particular game. This is that small size board. I think this was actually running in CPU only on a laptop. It may even have been a Chromebook. So this is running completely unaccelerated on that smaller size of Go that I was telling you about. Oops. and it doesn't loop, which is unfortunate. But you can see the variations that it's considering in the upper right, what it thinks is the most likely move to happen in the left side. And this is a pretty great tool if you're a Go player. You can really dig in and see what it's thinking about, why, what it likes, what it doesn't like. Pretty great. All right, so talking about our results. All right, so results. OK, so talking about the conclusions and the lessons learned, I kind of want to talk a little bit about the trends here that we've had, which is moving from GPUs to TPUs, and in this case, these were older GPUs to the newest TPUs, has been eye-opening. The ability for us to do more work with basically the same amount of electricity means that us users have our incentives aligned with cloud providers to use the newest and fastest hardware. Basically, there's no reason that we want people to use the older versions of the hardware, because the newer versions of the hardware will do the same work, will do more work with the same wattage, which means that we really want you to use the newest thing that you can. So as long as this holds, there's going to be this pressure for us to make our code go as fast as possible. And this is fantastic. In particular, when you're doing research, if you're trying to dial in these solutions, you need to be able to experiment as quickly as you can. You need to be able to try things that might have been too expensive to try otherwise. And so having this push to use the best price per performance and having the price per performance be use the fastest thing, not use the slower thing, means that we can really dial in the models that we're trying to build. We can really iterate faster on how we're going to test the various ideas we have for how to develop models. But what that means is you should plan for your pipeline to get faster. Again, we had originally bracketed that this would take us a couple months, and now we're looking at getting it done in a week or two. And that changed some of our core assumptions about how long we'd have to do a lot of the different steps in that pipeline. And it seems like that's only going to continue, so definitely you want to plan accordingly. That is the Cloud Edge TPU, which is the little USB gum stick on which we're going to make Minigo run, which I'm really excited about. In relation to this idea that your pipeline is going to be faster, we really want to try and make our models more like cattle and less like pets. Have you guys familiar with the cattle, not pets metaphor from containers? Some folks may be getting the idea. The idea being that containers let you reproduce the exact build of the software you're running. You can say that my server is interchangeable, that I can get more of them. I don't need to give it a name. It's not special. It's not a big deal if it dies or goes down or breaks and I have to rebuild it. In the same way, we'd like our neural network models to be like that as well, where if it takes you 3 months to do it, you get kind of possessive. Like, you really don't want to see anything happen to it. But if you can make a new one in a day or two, now you have this freedom and ability to experiment and try things. And it means that you can keep those changes much better isolated. With our early runs on GPUs that were taking months, it was very tempting to constantly monitor the dashboard, try and tweak some knobs, try and turn some dials here and there, and worry and fret over it. But it also meant that at the end of that process, how could I reproduce exactly that sequence of things that happened? Really hard. Having it all go faster means that it's all a lot more repeatable, and that's pretty great. Another thing that's pretty interesting here is that these reinforcement learning systems really resemble distributed systems. So I imagine a lot of folks here work in the cloud, and they're familiar with the idea that your individually well-behaved systems stop being well-behaved in tandem. And that's pretty interesting from a number of reasons. I think that there's sort of two ways that we go about analyzing why our systems are doing the wrong thing. One of them is from the code up, where we can look at the code and understand exactly what will happen. And the other way is from the behaviors that we see down, where we have to think about what's happening and generate a hypothesis and say, OK, if the load balancer is doing this, then we would expect this, and I can test that this way. Maybe you can't solve that just by looking at the load balancer's code and the server's. You have to generate a hypothesis and test it, and those are two very distinct steps. I think it's inductive versus deductive. And in a very similar way, neural networks and developing neural networks have the same problem, where you can't directly point at a line of code for why a model makes the decision it does. But instead, you created code that made that model, which means more of the top-down type of debugging. You still need to be able to look at specific code and try and figure out what's going on. But in this way, these reinforcement learning systems really resemble a lot of the distributed systems and the idea that debugging is a process of generating hypotheses, figuring out how to test the hypothesis in isolation, verifying, OK, well, I did this, I expected this, this other thing happened. What does that mean for my intuition about how these systems are working? All right, so let's sort of wrap things up a bit. There's two major parts of this, the machine learning part and the software engineering part. And I'm trying to focus in this talk mostly on the how part. How did we get to 90 petaflops? How did we monitor health? How do we get the performance that we need? How do we make it work? I haven't touched basically any of the machine learning parts. Why is the network this way? Why are these constants like this? Why is the network structured like this? Those why questions, those are pretty tough. But we can't really answer those whys until we have the hows nailed down. So if you have your neural network, your machine learning problems that you're trying to figure out the answers to these questions, obviously, those are going to be domain specific. But when you say, OK, well, how am I going to deploy and test these applications? How am I going to test my hypotheses? The answer there has been a cloud platform that's worked fantastically. So let's talk a little bit about the things that did work really well. So I've included a little Stackdriver dashboard that we used. Stackdriver was fantastic. We could just throw things to standard output and regex through them without any trouble. I mentioned cloud storage, also scaling way beyond the level that we talked at. So our early clusters were putting out maybe 50,000 games a day with a full-size model. With TPUs, we're putting out over 1 million games a day and still having to download and handle them all. And cloud storage has just been a champ. At some point, we're thinking about doing an integration with Cloud Bigtable, but that's still TBD. And in the meantime, cloud storage has just been we just abuse it. It's really wonderful. Kubernetes Engine and Cloud TPUs, as I mentioned, those basically worked out of the box. If you're interested in using them, it's a pretty great experience. Definitely sign up what you need to do. TensorBoard 1.9 has the latest release of TensorBoard. Will let you serve your TensorBoard dashboards right out of cloud storage, which is great. If you are trying to use the cloud TPUs, the profiling tools are easy to use. They're useful to dig into and find out how you can get the most performance out of those TPUs. So all of these parts of using the cloud stack went really well. As for those whys, I love this quote here from Alex Erpan. Reinforcement learning is really hard. He has this quote, if it turns out random, I have no idea if it's something I did or if I just got unlucky, right? We have some of these algorithms in the state of the art in machine learning right now that maybe a correctly working version with a different random seed will not converge on a solution. And that's kind of astonishing, that here's a successful result that's been published that only works 30% of the time. Obviously, AlphaGo 0 seems to be much more robust, but it kind of points out the challenges in testing these hypotheses and the need to be able to iterate and isolate and sort of formulate hypotheses and see if they work. This is kind of an amazing quote that I really like to think about. For me personally, I've been following in the footsteps of published papers where I know what is possible because Deepmind had published their papers. It would be much harder for me to, just trying to imagine if I was in their shoes, where I get a model that turns out pretty good, but not great. And I say to myself, well, can it be better? Or is this the best I can do with this approach? Right? There's a very big difference between exploring the unknown and reproducing the known. In my case, if I hit a ceiling, I can compare that ceiling to the ceiling that they described and say, OK, well, maybe I clearly have a bug. Whereas for somebody doing new research for the first time, it's going to be much harder for you to say, is this the ceiling, or do I have bugs? You really need to be able to be diligent and controlled and make sure that you are able to isolate the parts of your system and make sure that each of them is doing what you think. Does that kind of make sense? Great. Awesome. And lastly, I kind of want to quote about why I'm really excited as a Go player that all of these things are finally taking shape. I started Minigo after the AlphaGo paper was published, which I think was November of last year. And since then, Facebook has announced an open source version. They've just released a model. Tencent and other Chinese companies have been working on models which they've released with various degrees of openness. It's been very exciting to have these. And an open source project called AlphaZero has also been done where they've been trying to crowdsource all of the GPU compute needed. And it's been really excellent to have all of these different folks try to reproduce the paper with varying amounts of success. And it's really wonderful as a Go player to have access to these essentially oracles. Go players like to think of playing a game of Go as having a conversation, talking with someone. We have a great proverb that playing a game of Go with someone is like living with them for a year. And in that case, we have this new thing that is saying new creative ideas to us that we haven't really understood before. So if you are interested in learning more about the game of Go, definitely check it out online. There's a lot more resources. And hopefully it's going to be a lot easier to learn now that we have ways to understand it. We do try to hang stories on our moves that we play. And it's going to be a little bit easier for us to sort of do that and understand that as we have better tools to dig into. So thank you all very much. A big thank you to the folks who have helped donate their time to work on Minigo. That's Tom, Seth, Brian, and Josh. They all have been instrumental in making Minigo possible.